Okay, good day. This is Honors Algebra 2. I am Mr. McCully, and this is the presentation for Section 10-3 on infinite or finite geometric sequences and series. We'll talk about the infinite ones in the next lesson. So let's get to it. Today we're going to write a geometric series sequence as a function. We're going to use summation notation to write finite geometric series, and we're going to find the sum of a finite geometric series. So let's first talk about what the general formula of a geometric series sequence looks like. It is a sub n equals a sub 1 times r to the n minus 1, where a sub n is the nth term, a sub 1 is the first term, and r is the common ratio. You will note that this is a form of the exponential function y equals ab to the x. It looks very similar to that. In fact, the values end up being the same. So first thing, find the equation for the nth term of the following geometric sequence. And so what we're going to do here is we're going to start looking at this value, and we have to fill in the blanks for that general form. A sub n equals a sub 1 times the common ratio to the n minus 1. Now, one thing you might be saying is, why do you need this to be n minus 1? Well, if it were just n, it would be a sub 1 times r to the first, and then we would have whatever a sub 1 times r is. If we want this to be the first term, this a sub 1 to be the first term, then we can't be multiplying by any other values. So if I go 1 minus 1, I'll get 0, and since r can't be 0, anything that's not 0 to the 0 power is 1. All right. So I start looking at this value here. I'll say a sub 1 is equal to 1. And then I look for my common ratio here. So what times 1 is 3? Well, 3 times 1 is 3, and then 3 times 3 is 9, and then 9 times 3 is 27. So I can say that my common ratio ends up being 3. Now it's just a matter of filling in the blanks. A sub n, the nth term, is equal to 1 times 3 to the n minus 1. Now we wouldn't ever leave anything, let's put that back, 1 times anything. So our final answer will be a sub n equals 3 to the n minus 1. Put a box around that, and we'll say we're good. Next, geometric means. The geometric means of a geometric sequence are the terms between two non-consecutive terms of a geometric sequence. Example, find the geometric means for the following sequence. So we're going to look at this and we're going to attack it in a similar method to the way we found the arithmetic means of an arithmetic sequence. We're going to figure out what some values are. We know that a sub 1 is equal to 3. We know that there are 1, 2, 3, 4, 5 terms. So n in this particular instance is going to equal 5. And we know this value, a sub 5, which will be our nth term, is going to equal to 48. So if I go a sub n equals a sub 1 times r to the n minus 1, and I plug in the values that I know that my fifth term, the term that we're looking for here, is the 48th value, is 48. I know that a sub 1 is 3. I don't know what r is, but if I can figure out what r is, I will know the rest of it. And I know that my n, because this is my fifth term, is going to be 5. All right, so let's do some simplifying here first. So 48 equals to 3 times r to the 4. All right, so if I divide both sides by 3, so 48 divided by 3, 48 divided by 3 is 16. So I have 16 equals, oops, didn't mean to do that. Let's move it back. 16 equals r to the 4th. Well, how do I figure out what r is? I'm going to raise, A-I-S-E, both sides to the 1/4 power. And what that's going to do is when I use a to the x to the y, I'll get a to the xy, and then 1/4 times 4 will be 1. So 16 to the 1/4, and then r to the 4 to the 1/4, and that'll give me 4 times 1/4 is just r, and then 16 is a perfect fourth power. It is actually 2. And so I know that my common ratio is 2. So I could come up with an equation. I could say that a sub n equals 3 times 2 to the n minus 1, and just plug in. I can plug in for the second term, the third term, and the fourth term. But with 2 and 3, it's fairly easy. So our missing terms, 3 times 2 would be 6. 6 times 2 would be 12. 12 times 2 would be 24. And then 24 times 2 is 48. So these are our missing geometric means. All right, next question, or next statement here. To find the nth partial sum of a geometric series. So again, if I add up the first n terms of a finite geometric series, I'm going to use this expression where s sub n is the nth partial sum. So this is going to be the sum. A sub 1 is the first term of the sequence, and r is the common ratio. So the good news is we don't need to know the last term to solve this. All we need is the first term, the common ratio, and how many terms we need to add up. So that's pretty good. That makes life a little bit easier. So let's find the sum of the following geometric series. Okay, so I've got 1, 2, 3, 4, 5, 6, 7, 8. So again, just real quick, S sub n equals A sub 1 times 1 minus r to the nth over 1 minus r. So I've got 1, 2, 3, 4, 5, 6, 7, 8 terms. So n equals to 8 in this one. So we're going to find the sum of the first 8 terms. And the first term we recall is 10. And then 1 minus, well, what is the common ratio? What times 10 is 20? Well, 10 times 2 is 20. 20 times 2 is 40. 40 times 2 is 80. So I feel fairly confident in this that my common ratio is 2. I don't know why I put r there. The common ratio is 2. We'll raise that to the 8th power, and we'll bring that all over 1 minus 2. Now, I wouldn't expect you to do that in your head. So let's grab our graphing calculator, and let's go alpha y equals to bring up the fraction menu there. And the first term was 10, and then we're going to put parenthesis, and we'll go 1 minus 2 raised to the 8th power, and then we'll bring that parenthesis there, and then we'll just on the bottom go 1 minus 2. We'll hit enter, and we'll see that it is 2,550 is the sum of these numbers. So 2,550. All right. So this sum here, okay, well, we don't even have to do any of that work because we notice that this thing right there, that has the form a sub 1 times r to the n minus 1. And this value right here, that is our n because we start counting with 1. All right, so I can say that this thing is going to have 10 terms. The first term is going to be 3, and the common ratio is going to be 2. So that's a fairly easy one to calculate. So S sub 10, the sum of the first 10 terms, will be equal to the first term 3 times 1 minus the common ratio, which is 2. And then we're going to take that to the 10th power, and we're going to put it all over 1 minus 2 again. The common ratio is again 2. And we'll go grab our graphing calculator. Again, alpha y equals to bring up the fraction menu, 1. And then our first term in this one was 3. And then it was 1 minus 2 raised to the 10th. And we'll bring it down to close that parenthesis, and then it'll be all over 1 minus 2 again. We'll hit enter, and we'll get 3069 as the sum. All right, let's talk about a application problem. The evil Professor McCulley releases his deadly McVirus into the world by ejecting one person on day 1. That person infects 3 people. and they in turn infect 3 people each day after so on and so on. What is the total number of people infected on the 15th day? So let's set up a sequence here. And so my first term is 1, and to that, so on day 1 we've got 1 person infected. On the next day we'll have 3 more because this person was already infected and he infects 3 more people. Now, on the 3rd day, this group of 3 people infect 3 more people individually, we get 9. And then the next one would be 27, and so on until the 15th day. Now, we don't have to calculate that because our formula doesn't require it. So all we're going to do is we're going to go S sub 15 is equal to 1, the first term, times 1 minus, well, our common ratio in this one is clearly going to be 3. We're going to raise that to the 15th power, and then we'll go 1 minus 3 again. We'll put that in our graphing calculator. So math, nope, not wrong, alpha, y equals, to bring up our fraction, we'll hit 1. First term was 1. 1 minus 3 raised to the 15th power. Close that parenthesis, all over 1 minus 3. This should be a pretty big number. So 7,174,453. 7 million. It's 7,174,453. Put in our commas and people infected. That's our final answer for that. All right. So we are finished. And the Macaulay fun fact of the day, Mr. Macaulay's first personal computer was the Apple IIc, Christmas of 1984. And this computer had the distinction of being the first for-sale model that had a built-in hard or floppy drive. And now we're getting computers without any drives at all again. It's kind of crazy. And yes, I know it was an Apple. But I was 13 at the time, so I was young and I didn't know any better. And now we can get rid of those garbage computers. That's all I have for today, folks. Have a good day. Bye.